Right then, can a Raspberry Pi 5 really spot number plates on the mad streets of New York, or is it going to be more confused than me in a roundabout in Inverness? Let's find out. Welcome back, folks. In part 1, we built and set up a Raspberry Pi with the AI hat. Today we're taking it a step further. First we'll run a few pre-trained models, then I'll show you how to build a dataset and train up a segmentation model for number plate detection. And to finish off, we'll fire our New York driving video through the Pi and see if our wee model keeps up. Let's crack on. The first thing I want to get into is I want to find a way to just run inference on some videos and save a video to disk with overlays of what was found. So I have gone and forked the Halo Raspberry Pi 5 examples repository. This is actually really good for getting started, so I definitely recommend going to the main repository here, and you can really get your teeth into lots of different examples and understand how it works. One slight drawback with the design of it is that they have this Raspberry Pi specific repository here, which heavily relies on this Halo Apps infra repo, which has a lot of other sort of plumbing for the AI accelerator resources. And if you want to make your own tools, you kind of have to make changes to both. So actually, like GStreamer pipelines are defined in this, and then there was like some other just specific basic calling scripts in here. So I've just basically decided to fork the repo and just bring in this Halo Apps in here. So by all means don't do this, but this is just what I did to get things easily working from a single repository. So what I've done is I've created a new pipeline called detection file simple, and that just runs a pre-trained model on a model which you define and an input source which you define, like file or camera, Raspberry Pi camera or USB camera, and yeah, that's it really. So this is the main calling script essentially that just calls this GStreamer detection app file with this callback here, which just can do some stuff. You can see here it's going through user data, printing out frame count on a per frame basis, getting the buffer, looking at the detections and printing out detections to the terminal. So that's it really. However, I've also modified and created a new app in here called detection file simple, which is essentially just a copy of this, which adds in file pipeline to here. I think this is how you use GStreamer. So you essentially create a pipeline which accesses things on a frame by frame basis, and then you can kind of stream stuff into separate parts in the pipeline to do different things. This is not a new approach, but it's certainly quite performant, and I think that's what you need with Raspberry Pi. So you can see here, essentially at the very end, this is the thing that really matters. We have a source pipeline, which can be either from file or from camera. Then we run a detection pipeline, which is running our model. Then we have this user callback pipeline, which we pass from the calling script. And then I've added overlay pipeline and file sync pipeline. So this will draw the results. These are basically just off-the-shelf pipelines that have already been provided by Halo and GStreamer. So we can essentially, run over some videos and see what we get. So let's dive into just running a already pre-trained dual model on a test video and see what we get. Okay, so this is a test video that we're looking at. It's a promotional video for a boat. So I think we should use this and send it through our pre-trained model and see what we get. Essentially just going to be the YOLO v6 nano model, I think, that they're providing, which is just trained on the Cocoa dataset as far as I'm aware. So we could just run it through this frame by frame and see what sort of output we get. So we can SSH into the Pi, go to the directory with the Pi examples, and then we have to run source setup env.sh. Let's run this through detection file simple. So this is just going to start putting this through frame by frame. There we go. It's working away. You can see it's found some boats already. That's a good start. Some cars, airplanes, not so sure about that. Some more boats, people. Okay, so inference is finished. Let's have a look and see the results. So it's taken 2 minutes 33 seconds to process 3864 frames, and after doing a little bit of maths, that's 25 frames per second. And yes, we're just using a nano model, but it's still impressive that our little Raspberry Pi is doing a full pipeline with inference 25 frames per second. So there's options here. It seems like it could actually be a viable solution for real world, real-time detection. The question, of course, is how accurate are these detections? So yeah, found a boat, airplane, not quite, obviously hasn't been trained on outboard motors. Yep, picking up a boat, lots of boats. I mean, yeah, incorrectly detecting people, surfboards and toilets. But as I say, you have your own specific training set with outboard motors, and you can start with the Cocoa as a start point. Yeah, boats. That boat in the backgrounds, they are very small. One interesting thing is the output video is not the same dimensions as the input video, but I'm sure I could go into more detail to try and work out why this is. But general results are quite impressive. Quite good chairs, people. I mean, general performance is pretty good given the fact that this is using just something pre-trained, old generation YOLO v6 architecture, working relatively well. So I think the next step is we're going to create our own dataset on oslo.vision, and then we will export that, train YOLO v8 segmentation model, and then we're going to try and convert that to a HEF format, which is what the Halo Raspberry Pi accelerator uses. And then we can see if we can run some inference on some videos to extract some number plate information. Okay, let's get our dataset ready. So on Oslo Vision, we have a number plates dataset, and let's upload some images of some number plates. So I can just show you the process that I'm going through to create the dataset. So yep, we're dragged in some images of cars number plates. Let's save and continue. Assign that to me. You can see I already have some I've already created earlier, but I'll just show you the annotation process using the Auto Poly tool. This looks like United Kingdom based by those number plates. So you can use this tool to automatically find the number plates, which makes the annotation process a lot better, because in this case we're going for segmentation for number plates as opposed to bounding boxes as traditionally used, because well, they're often not at like a perfect 90-degree angle. So yeah, we're just going to go through these images and do all the annotation of number plates that we find. And then just build up a data set, and then we can then use that data set to train a YOLO segmentation model. We're going to go for the YOLO v8 small segmentation model. So it's not the nano version, we're going to go for the small version because it looks like it's supported on the Halo hardware that we're using on the Raspberry Pi AI accelerator. So we're just going to train the model in Google Colab, and then we need to actually convert the model to the native HEF format that the Halo uses. Unfortunately, this is going to have to be done on an x86 machine that we have in the test lab here at Oslo. You could potentially do it on a large Colab instance, but you definitely cannot do it on the free Colab instance. So yeah, we've gone through, annotated those images, and now we're just adding them to the dataset. So yeah, next step is doing some training. Okay, let's do some training. So the dataset is complete, or at least an initial version. It's not very large, but I think it's enough to show training a model. Yep, increase the validation size slightly. Exporting to the YOLO segmentation data type. You can also export to Coco or VOC if you want. Yeah, train other models that require different annotation format. You can also just export as YOLO bounding boxes if you want to train like a standard object detection model from segmented data, which can be useful as well. Right, that's our export complete, 349 images. Let's carry on. You can download that if you want, but now we're going to train a model, so we're going to just do this on Colab for ease of use. But first, let's connect to the runtime, and we'll run the NVIDIA SMI command to make sure that the GPU is connected. Great, there we go. I'll install the Ultralytics library. This is all standard stuff if you look at some of the other videos where we've done training, so I won't go into this too much. We'll just try and jump through it quite quickly. If you want to use, if you want to see more information yourself, feel free to download the notebooks and play around yourself. Check the dataset looks reasonable. Yes, it does. There's some of the stuff we just annotated. Let's train. Just a little hack to make sure there's no issue with previous versions of Ultralytics. Changing the settings, which is applicable if you're running on your own hardware. There we go. So we're using the YOLO VS seg.pt trained weights model architecture, and then boom, we're going to train for 100 epochs. Okay, training is complete. Looks like pretty cool metrics we got there. High box precision and recall. Let's have a look at the confusion matrix. Looking pretty good, 77. There's just a couple of other, 4 versus 77, very nice. It looks like we could train for a few more epochs, but generally looking at this validation batch prediction stuff, looking pretty nice actually. Let's run some predictions on the test set. This is data that the model has never seen. Let's visualize those predictions. Very nice. Alright, so we've trained our model. Let's export it from PyTorch to HEF format, which is Raspberry Pi specific. We're going to open it in our own machine, train our own machine here, because the Colab machines don't have what we need. It errors out with missing packages and not enough RAM, etc, etc. Maybe with a paid high power package it might work, but I'm just going to show you actually running it and doing the conversion on your own hardware first. So you don't always have to use other people's hardware. You can just use your own. So yeah, it's for converting your PyTorch to .hef format, and this is specifically aimed towards the Raspberry Pi AI 13 tops. You might just need to change one argument from Halo 8L to Halo 8 to use on the 26 tops version. You can see that, this is on a 4060 Ti, 32 gigs RAM, 2204. It doesn't run on Colab as I mentioned. You start by copying your PyTorch weights, making sure they're in the same directory as this notebook. In this example, we're going to pull our dataset from also.vision and use that for the calibration images, which is the process which is used to do the conversion. If you're not using also for your dataset, just upload a folder of images that can be used. So yeah, first step is to create in this case, we're SSH'd in remotely using VS Code, so remote editing, and then in that we're using this basically this notebook. So we've set up a virtual environment. I really strongly recommend that you do use a virtual environment, so it's much easier to install stuff. You see we've got a little terminal here. It automatically puts you into the VM after you set it up on the Python notebook. So yeah, what we're going to do now, let's install these dependencies. Unfortunately, this is not the cleanest of dependency setup. It could be a bit nicer experience, but what we're doing is we're pulling down the Halo Dataflow compiler from a personally hosted wheel. Otherwise, you have to sign up for the Halo developer zone and have access to files through there. Also, we're going to clone the Halo model zoo repository, which is also an official Halo AI tool. Now we're going to sudo apt update and install a couple of dependencies, GraphViz and GraphViz dev. On top of that, we're going to then, within our virtual environment, install the Halo Dataflow compiler. Then we have to do something really quite horrible where we're going into the Halo model zoo and then we're specifically checking out a specific commit hash because the Halo 8 models are no longer supported in the repo. It says there's a different branch where the code is, but that branch does not exist, so I've had to check out a specific commit hash, at which point we then install the Halo model zoo. There's probably a nicer, more official way of getting this stuff installed and working, but this was the easiest reproducible way that I could find. So that takes a couple of minutes to do. While we're waiting, let's fill in our credentials for Oslo Vision. So we're just going to put in some API connection details so we can pull down our dataset to be used for the calibration images setting for the HEF conversion tool. There we go. Okay, that's the project identifier. We're going to dataset version 2, and I'm going to create some API access to my account. By the time you watch this video, this set of credentials has been revoked, so won't work for you. Okay, looks like that's finished. It took about a minute and a half. Now let's install Ultralytics. We will use that to convert the PyTorch model into the ONNX format, which is the first step in the conversion process. Alright, 44 seconds, there we go, it's installed. We've got our home. Now we've set up these credentials for pulling down our dataset. Let's pull that down. Off it goes. There we go, 4 seconds, not too bad. Number plate locations of our calibration images. Now let's export from best.pt. I need to fix the path there. There we go. Just these weights are in the same directory as the notebook. We're exporting to ONX, expecting 640 by 640 input shape, and it's for the version 11 of ONNX that we are exporting for. Good stuff. It seems to be talking about YOLO VAS seg, which is the correct architecture that we are working with. Now let's go to the segmentation training part of the notebook. So we're setting the ONNX model, we're setting calibration images to dataset path train, and our number of classes is 1. As you can see, if we go into the number plates and then classes here, we just have 1 class, so we're just training with 1 class, well, converting with 1 class, sorry. Now for a one-liner for the Halo model zoo compile step, we need to pipe yes to Halo MZ compile so that it doesn't actually ask us for some input in the process. We're saying our checkpoint is the ONNX model, hardware architecture, Halo 8L, calibration path of the calibration images, number of classes is 1 that we're passing, and we're also asking it to use the performance mode for compiling. So compiling, let's say. So looking at now, it's working away. There's various warnings about different software versions. We're 2204 when it's asking for 2004. some various packages are not installed. However, yeah, we're just going with this because it actually just works. You see, because you can't really be expected to have absolutely required versions of everything. There we go. So it's working away, and believe it or not, this will take around about 1 hour to do, which is very surprising given the fact that training only took about 20 minutes or something. So yeah, let's go away, have a cup of tea, and come back when training is complete. Alright guys, now let's try and see if we can do something on the Raspberry Pi. So we've converted our hef file, let's use it in anger. So I've made a little instance segmentation, or bastardized existing instance segmentation thing that I found in the Halo application code examples repo. I've essentially modified it to just run in a synchronous manner to pull frames from video input, and then it will run inference on the frame and then output to another video file with the annotations written onto each frame. So this can just show us essentially our segmentation model in action, and all influence being performed on the Raspberry Pi. So what we're going to do now is have a test video, which is video of a person driving through New York City. So it's perfect, there's lots of cars everywhere. So we're just going to process a 2-minute chunk of that and see kind of how we do with finding number plates in that. So this is like really quite exciting because, you know, we've trained this thing from scratch and we're running it on a decent sized 1080 video. So yeah, initially this was I had an initial version of this which was running a lot of different queues and threads, but the problem I was having is it was very easy to just use up the whole memory in the machine, so I've simplified it into a single thread basically. So this is probably slower processing wise than it needs to be, and if we used the GStreamer implementation that they often tend to recommend, maybe that would be a better approach. But I couldn't actually find a GStreamer specific implementation of YOLO V8S segmentation. This was the only code example which is using segmentation. So with further ado, we could go through this code here, but I think just have a look in the Oslo repo if you want to go into details. This video's been going on long enough. So yeah, let's just run some inference here, run our script, and just start processing the NYC Wii video. So yeah, it's just going to sort of churn away. This is all running on the Pi. Let's have a look at what resources it's using. So impressively, I mean, using a lot of CPU, but only 4% memory, which is great news. So it just shows the synchronous method is really quite nice with memory. So before I was getting up to 80-90% memory usage on this 8 gig Pi, which was causing it to lock up. So now it's just working away. Come back later when it's done and have a look at the results. Okay, there we go. Inference is complete. And now we've got the video up as a preview. We're just gonna sit back and relax. See quite a few of these number plates as they are detected. They will appear as annotated. See them with a bit of opacity. It's very impressive here. Almost all of these number plates on cars passing and a front are being detected at some point or other. This is very useful. One thing I would say is that despite the fact that they're being, oh no, that's not too bad. I think you could expect OCR to be able to find this here. It's reasonable. This has also been detected here. And this has also been detected. So we've got 3 detections in this frame, all of which I think would actually work, and OCR would actually work on them. So this is actually very, very nice. One thing I think that could be useful is actually recording at 4K and trying to infer on these 4K images if the memory would allow it, because then I think you'd get much higher number plate resolution. So when you actually do get these detections, the chances of running OCR in them are a lot higher. So I think this would be an example where I think running a 4K camera would really help. I think we can investigate that a little bit more in the next part of the series. So yeah, almost all of these parked cars we are detecting as they get closer to the camera. I do see some rogue detections, like sometimes signs are found, so this could be a sign that we need to do some more potential active learning of maybe adding a sign class or something like that, or the alternative is to do more of a pipeline based approach where you find cars first and then look for number plates within there. But this very simple method seems to actually work surprisingly well. So yeah, that's really it for this video. I think we've shown that you can really actually do some great stuff with this little AI accelerator. I would say that the code examples are okay, but the company themselves seem to be moving forward to the next generation of their Halo accelerators, like the 10s and the 15s or something along those lines. So a lot of the GitHub repos at the moment seem to be starting to be geared towards that, as if they've almost forgotten about the Raspberry Pi AI accelerator. So I'm not sure whether this is like kind of a dying product or it's like something that they're really behind from a company perspective. But it's still interesting what can be done with the Raspberry Pis, and I think they are like a great alternative to using NVIDIA Edge hardware. I mean, I would say that the NVIDIA Edge hardware is kind of the market leader in like Edge computer vision, but it's nice to have alternatives. Okay, that's it for now. In the next video, we're going to see if we can build something a little bit more advanced with Raspberry Pi and cameras. So we're going to try and record some of our own videos and see what we can do with that number plate information that we gather. Okay, bye for now.